Michal Korch of the University of Warsaw. We'll talk about the class of perfectly null sets in transitive version.
Thank you very much. And also I would like to thank the organizers for this opportunity to give this talk. Also I would like to say that because of this nice weather we have here, I also developed a cold, so I apologize for my voice, which is not as clear as I would like it to be. Okay, so, and also some of you might have heard my talk in Hejnice during the winter school, so this one obviously will be quite similar, although some new elements will be there also. So, I will be talking about the class of perfectly null sets and its transitive version, and it is my joint work with Tomasz Weiss. If you are interested, you can find a preprint of our paper on my webpage. It can be googled. Okay, so let me start. I will be talking about some classes of special subsets of the real line. We'll be working in the Cantor space. So among these classes, the two most known, I think, are the class of perfectly meager set and universally null sets. So a set is perfectly meager if its intersection with every perfect set is meager in this perfect set with respect to the subspace topology, and the set is universally null if it is null with respect to any finite Borel diffuse measure. Another classical notion is the notion of class of strongly null set, of strongly measured zero sets. A set is strongly null if it can be covered by a sequence of open sets of any given sequence of diameters. So, theorem of Galvin, Michalski, and Solvay states that set is strongly null if and only if it can be shifted away from any null set, which allows to define from any meager set. Thank you. Which allows us to define a dual notion of strongly meager sets. Set is strongly meager if it can be shifted away from any null set. Around 2000, Piotr Zakrzewski proved that two earlier defined by Grzegorek classes of special subset actually coincide and have some properties actually dual to the class of universally null sets. And before that, those two classes, universally null sets and perfectly meager sets, were considered to be somehow dual. Those are differences that have been proved. For example, the class of universally null sets is closed under taking products, and it is consistent that the class of perfectly meager set is not closed under taking products. So this class of universally meager set is closed under taking products, and the set is universally meager if every Borel isomorphic image is meager. Okay, and finally, Nowik, Shepard, and Weiss, studying some additive properties of special classes of class of special sets of the real line, came up with a notion of perfectly meager in the transitive sense sets. I will come to definition later on, but as you can see, there are those inclusions on the category side, and for each of those inclusions, it is at least consistent with ZFC that this inclusion is proper. So the goal of this talk is to try to define classes which can appear in these gaps on the measure side, which can play roles dual to the class of perfectly meager sets and perfectly meager in the transitive sense sets. Okay, so the plan is the following. In the first part, I will talk about perfectly null set, give some definitions, make some simple but important observations, and then I will state the main open problem which still stands. I will talk about this problem for a while, and in particular I will just deal with a simpler version of this problem. And in the second part I will talk about perfectly null sets in transitive sense. Again, I will start with some definitions, show you 2 or even 3 theorems, and conclude with some further open problems. Okay, so to define what we should mean by a perfectly null set, we need a canonical measure on a perfect set. So let's start with it. It will be convenient to see the Cantor space as simply as an infinite binary tree. So then a perfect subset is just a perfect subtree like this one. So given such a perfect set in the counter space, you can easily see that we have a canonical homomorphism between the whole counter space and this perfect set, simply given by homomorphism of trees. Okay? So now given a subset A of P, we can easily define a measure, we will call it canonical measure on P, mu P of A, as the Lebesgue measure of the preimage of A under this homomorphism. Obviously, A is measurable if and only if the preimage of A is measurable in the Lebesgue measure. So, for example, the measure of the basic set given by the sequence 110 with respect to mu p is 1/4. That's the counter image of this set. Okay. So now we will say that set X is perfectly null if for any perfect set measure mu p of p intersected with X is 0. I will usually draw this intersection part simply assuming that mu p is a measure on the whole counter space with support p. Okay, so now some basic but important observations. Every universally null set is perfectly null. If a set is of measure 0 with respect to any Borel diffuse measure, then obviously it is of measure 0 with respect to mu p for every perfect set p. And recall that set X is in Warszawski ideal as 0 if for any perfect set we can find a perfect subset Q in P such that Q is disjoint from X. So every perfectly null set is in the Warszawski ideal. Again, it can be easily seen if set X has measure 0 in P, then P minus X is of positive measure, so we can find a perfect subset of it. Okay, so we've also proven some further properties of this class of perfectly null set, but any of these properties does not allow us to distinguish this class of perfectly null sets from the class of universal null set. So the open standing problem is whether actually those two classes are different. Is it consistent that there exists a perfectly null set which is not universally null? I do not have an answer for this problem, it is open, but I would like first to show you what is happening with this problem on the category side. So on the category side, all known arguments proving that there exists a perfectly meager set which is not universally meager use the idea of the Usin function. So, or some similar ideas to it. So, the Usin function is a Borel isomorphism onto its image, defined by Usin and then studied by Sierpiński in the 30s. And it has this property that if L is a Usin set, then the image of L is perfectly meager, image under this Usin function. Recall that a set is Usin set if it's an uncountable set and its intersection with every meager set is countable. Okay, so now assuming that there exists a Usin set which is consistent with ZFC, for example, under continuum hypothesis, we see that the image of this set under this Usin function is obviously perfectly meager, but cannot be universally meager because the Usin set itself is not meager. Okay, so a natural question arises: does there exist a measure counterpart to the Usin function? I do not have full answer for this question, but only a partial one. I will just flash a proposition which is quite technical, so I will spare speaking about the details, and I do not expect that you will read this proposition truthfully, but it says that even if there exists such a function, such a counterpart, it cannot be constructed in a similar way to the way in which the Usin function is constructed. Okay, but we can ask another question which is quite related, because we can consider products we can consider perfectly null sets in the product of of two Cantor spaces using just the natural canonical homeomorphism alternating the coordinates. So the related open question is whether every product of two perfectly null sets is perfectly null. Obviously, if it's not, it gives the answer to the main question, because the class of universal null sets is closed under the product. But again, I do not have an answer, but I will solve this question for a simple case. We'll come to this in a moment. And the thing I would like you to notice is just a duality of what will happen in my proof to the case of the category. So again, this problem on the category side was quite a long-standing open problem, whether a product of two perfectly meager sets is perfectly meager, and was solved in the 90s by Retzlaff, who proved that it is consistent with ZFC, especially if there exists a losing set. Then the class of perfectly meager set is not closed under the Lie products, and he just constructs a perfect set in the product space and shows that given a losing set in this perfect set, its projections of this losing set are perfectly meager. So the product of those projections cannot be perfectly meager because it contains a losing set in a perfect set. Okay, so what's my idea of simplifying this problem? I need one more slide of definitions. So given a perfect set, I will note by split IP the set of all finite sequences which are the splitting nodes in this tree of level I, and I will note by Sy of P the minimum length of a sequence of a splitting node on level I, and capital Sy of P the maximum length of such a sequence. So in this case, for example, S2 of P is 2, and capital S2 of 3 is P. Yes, let's call it. That's 2, and that's 3. So, my idea is to require a set to be null only in some simpler perfect sets. In this case, I will call a perfect set balanced if the smallest length of a splitting node of level I plus 1 is greater than the maximum length of the splitting node of level I, so the splitting levels do not overlap. And I will say that a set X is balanced perfectly null if for every balanced perfectly null perfect set measure mu P of X is 0. So now just let's notice that those two classes, the balanced perfectly null sets and perfectly null sets, are fairly different. For example, if there exists a perfect Sierpinski set, then there exists a balanced perfectly null set which is not perfectly null. Recall that Sierpinski set is a dual notion to the losing set. A set is Sierpinski set if it's uncountable set which intersected with any null set is countable. Okay, so simple proof of this theorem, just simple combinatorics. Take such a finite tree K of height 3 and build from it a perfect set E, just stacking those finite trees one over another. So it is quite easy to prove that this set E has the following property, that if B is a balanced perfect set, then either measure of E in B is 0 or measure of E in B is 0. Have I said twice the same? No, I don't know. Either measure A with E with respect to mu B is 0 or measure of B with respect to mu E is 0. Okay, so if so, take a Sierpinski set in E. So obviously S is not perfectly null, But if B is a balanced set, then either E is of measure 0 in B, so S is of measure 0 in B, or B is of measure 0 in E, so S intersected with B is countable, so S is also of measure 0 in B, so S is a balanced perfectly null set, but it is not perfectly null. Okay, so finally, let's go to the simplified version of the problem. So we ask whether every product of two balanced perfectly null sets is also balanced perfectly null, and the answer is consistently not. If there exists a Sierpinski set, there are balanced perfectly null sets X and Y, which have the property that their product is not balanced perfectly null, and the proof resembles highly the proof of Retzlaff, because we construct a balanced perfect set P such that its projections are the same, and let's denote this projection Q, and Q has the same property as the set E from the previous proof. Namely, if B is a balanced perfect set, then either mu Q of B is 0 and mu B of Q is 0. So now, and moreover, this set P has the following property: if A is a subset of Q with measure 0, then its measure, then A cross the counter space is of measure 0 in P. So now, given a Sierpinski set with respect to mu P, let X be the projection of S, and suppose that B is a balanced set, then either Q is of measure 0 in B, so X is of measure 0 of B, or B is of measure 0 in Q, so the pre-image of projection of Q intersected with B is 0, so S intersected with this pre-image is countable, so X intersected with B is countable, so measure of B in X is 0 also in this case. So X is balanced perfectly null, and analogously the other projection of S is balanced perfectly null, but their product contain the Sierpinski set, so cannot be balanced perfectly null. Okay, so let's move on to the transitive version of this class. So recall that a set is perfectly meager if it is meager in every perfect set, in the sense of subset topology. It may seem somehow superfluous to say that it is perfectly meager if for any perfect set and any T there exists a covering of sigma set F, which is meager in P translated by T. This superfluous fact and the question of Shepard's of whether the algebraic sum of strongly null and strongly meager sets is always in the Warszawski ideal motivated Nowik, Schippers, and Weiss to give the following definition. A set is perfectly meager in the transitive sense if, and now we switch quantifiers from this superfluous sentence, if for any perfect set P there exists an F sigma set F covering X, such that for every T, F is meager, so F is meager in every translation of P. And in subsequent papers, Nowik, Schippers, and Weiss proved that every strongly meager set is perfectly meager in the transitive sense, and that every perfectly meager in the transitive sense is universally meager, and also proved that those inclusions are consistently proper. We give a similar definition, dual one. We'll call a set perfectly null in the transitive sense if for any perfect set it can be covered by G delta set G, such that every translation of G is null with respect to measure mu P. Obviously, it may happen that, impossibly may happen that this is not a sigma ideal, but let it be so. So we would like to know whether every strongly null set is perfectly null in the transitive sense, and whether every perfectly null in the transitive sense is universally null, and if so, whether those inclusions are consistently proper. So now I will show you 3 theorems, 2 of them with proofs, which partially solve those questions. So firstly, every strongly null set is actually perfectly null in the transitive sense, and the proof is quite straightforward. So let's just quickly move through this proof. So if X is strongly null and P is a perfect, so recall that X can be covered by a sequence of open set of any given sequence of diameters in a such way that every point of X is covered by all but finite of the sets AN. So let's take epsilon n less than 1 over 2 to capital S n of P. In this case, if a set A has diameter less than epsilon n, its measure in P always is less than 1 over 2 to n. So always it means that this set, even translated by T, is of measure 0 mu P, so it can be taken as this required G delta set from the definition. Okay, so the next theorem is just a last-minute theorem, because my co-author Tomasz Weiss called me like a day before my departure to this conference and said that he finally managed to clear all details of this theorem. So fair enough, I have put it as a theorem here, though I haven't seen the full proof of it, but hope it's okay. So it is consistent with ZFC that there exists a perfectly null in the transitive sense which is not strongly null, and this happens when we take a model which is obtained by a countable support iteration from Matthias forcing of length omega 2 and a set which has cardinality aleph 1. One part is obvious because it is a well-known fact that in this model Borel conjecture holds, so every strongly null set is countable, so X is not strongly null, and the other part seems like it can be done because this perfect set and the set X appears in some intermediate state. Okay, so but still we can ask a question whether in every model of ZFC there exists an uncountable perfectly null in the transitive sense set. Okay, and final theorem, it has quite an interesting proof, so let's quickly move through it. The proof is based on a method which first appeared in a paper of Retzlaff and is the following. First we construct two disjoint perfect sets which are linearly, union of which is linearly independent over Z2, and let's read the theorem. If there exists a universally null set of cardinality continuum, so we can assume that this set, universally null of cardinality continuum, and existence of such a set, by the way, is independent for ZFC. So we can assume that this set is included in C. So now enumerate all G delta sets with elements of this set X, and choose Yx in D translated by X, and this is the fun part, in such a way that if only it is possible, Yx is not in Bx. If it's not possible, just choose any Yx in X plus D. Okay? And denote by Y the set of all Yx's. So now notice that plus is a homeomorphism between C cross D and C plus D, and that projection of the counter image of Y is X. So since the measure can be mapped through this mapping, also Y is universally null. So now aiming a contradiction, assume that y is perfectly null in the transitive sense. So take perfect set D, and from the definition, x can be covered by y can be covered by a G delta set. So there exists a set such that y is covered by Dx in such way that for every t, mu d of this translation is 0. So take t equals x. We see that we haven't managed to achieve this one. So d intersected with bx plus x is d. So actually measure mu d of bx plus x is 1, which is a contradiction. Okay. So we wanted to know whether those inclusions hold and whether, if so, they are proper, and we proved that the first inclusion holds and is proper, and we proved that if the second inclusion holds, it is proper. So the remaining question is whether the second inclusion holds. And finally, also, there are some open questions concerning additive properties of this class, just motivated by the dual facts proved by Novick Shippers and Weiss. So, for example, we do not know whether if x is strongly meager and y is perfectly null in the transitive sense, then x plus y is in the Warszawski ideal. Okay, that's all. Thank you very much for your attention.
Questions? Remarks? Answers to the question?
Especially answers, would be nice.
Well, at least let's hear it.
Thank you.
So today's session is closed.